Good morning to all of you. This is Mark Richardson speaking from Vibrant Technology in Scotts Valley, California. It's 9 o'clock in the morning, so I'll say good morning to those of you that are on our time schedule. Some of you, I'm sure it's late at night or maybe in the middle of the night. Anyway, today we're going to spend an hour together in this webinar and look at some of the new features in MEscope. The option that we're going to use is something called FaCTs, and FaCTs is an acronym for Fault Correlation Tools, and it is part of our new options to MEscope that are used for machine surveillance or environmental surveillance or qualification testing. But I want to just show you some of the technology today, and we're going to use it to identify and quantify some unbalance cases that we've created on this rotating machine that you can see in animation on the screen right now in MEscope. So we're looking at MEscope, and this is a project that's been set up with a photo model. And let me go back for a minute and just review with you what we're going to talk about today. Let me start with the price list, and I'll put MEscope down and put up our price list. Oh, it's not coming up, Brian. Maybe I'm not going to be able to do that. Let me go ahead and bring MEscope back up and show you a schematic of this software system, which is a little bit different than maybe you're used to if you're an MEscope user. First of all, let me just show you this technical paper that we wrote back in 2009, and again, I'm having trouble sharing the screen. It doesn't want to leave it up. Brian, is there something I can do to put it back up? It's using it's a PDF, so it apparently doesn't want to share the screen with a PDF.
Yeah, I don't know if anything.
Well, let's just move on, and I guess I can't show you that technical paper, but it's one of the technical papers from 2009 where we detail some of the calculations that we do in order to identify and qualify or quantify the amount of unbalance on a machine. Let me show you some pictures here, and maybe we can get them to come up. All right, okay, well that one came up. Here is a block diagram of what we used to call Mechanicom. We still use that term, but this is MEscope in a monitoring environment where we're actually monitoring vibration on some machinery. And the three different options, and we call them series, that we've added to MEscope are the machine surveillance series, the environmental surveillance series, and the qualification testing series. Now, each of those software options is simply additional software that runs, that is added to MEscope, so that when MEscope runs under macro program control, which is a new feature in MEscope, and we'll look at that in a minute, MEscope can archive data into a much larger database. Now here it's called the Mechanicom database. We still use that term. That database is much larger than the MEscope database, and it allows us to archive data and then trend it and do other post-processing with it. So we're going to look at the software that allows us to look at the data in the database, and we call that console. Here you can see it's called Mechanicom console. Now, as I said, we have 3 different options of the console and the database, and we call them machine surveillance series, environmental surveillance series, and qualification testing series. So these are new series of MEscope together with these options, just like our visual engineering series that we've had for many years with the MEscope software. So in this environment here, or in this picture, MEscope is actually running in a solid-state computer in one or more of these suitcase boxes, and it's deployed out in the field to measure vibration on machinery. So we're going to simulate a situation just like that today in our webinar, and we're going to archive ODS data, what we call order tracked ODS data, into the Mechanicom database, and then we're going to use the FaCTs software, which actually runs in the console, to process the data that's been archived and identify which unbalanced case is being indicated by the ODS data that's being acquired down here in the box. So that's the idea. Let me go and show you a few more pictures here of the test setup that we took data from. So we're going to use pre-recorded data, ODS data. This data was obtained from some measurements that we call ODS FRFs, and those are output-only data from the accelerometers on this machine. So you can see the various accelerometers. There's one here on the motor, that's a triaxial. There's one on this bearing block, and then another on this bearing block, and each of those is a triaxial accelerometer measuring motion in X, Y, and Z. Down here on the base plate we have another triaxial accelerometer right here, and then over here is a uniaxial, and in the back is one more uniaxial. So we've got a total of 14 measurement channels or degrees of freedom in the ODS that we're acquiring data on and then post-processing with MEscope. So here's another picture of the machine setup, and then finally here's the different cases that we're going to look at. Actually 8 different cases. The first case is when the machine is in a balanced condition with no weights, and then we're going to create unbalanced conditions by adding small screw-in weights to the 2 rotors that you see indicated here. One's called the inboard rotor, the other the outboard rotor. So we're going to create different unbalanced cases, and then we'll see how the FaCTs calculation in the console software can actually identify from the ODS data which of those unbalanced cases we've simulated. So let me go back here and start MEscope, and you can see here that we've created a bunch of hotkeys, several hotkeys up here, and hotkeys are used now in conjunction with our macro programs to control MEscope in an automatic fashion. So we can set up MEscope if we put it in, deploy it to the field as a continuous monitoring system, or in this case we're going to control the archiving of data into the Mechanicom database with the use of these various hotkeys. So you can see that each one of them has a title. This one here is called balance, so that is my case number 1. Case number 2 is a small inboard unbalance. So we added a small weight to the inboard rotor, and then the next one is a small outboard. So this is the 3rd case. The 4th case is a large inboard, so we added a larger weight to the inboard rotor. And then large outboard. Finally, we added weight to both rotors with 0 degrees. In other words, they were both located, the unbalanced weights were located at the same position on each of the rotors. So we'll see in a minute when we look at the data. This is the most extreme case of unbalance, where the unbalanced weights are causing the machine to vibrate with the largest amplitude. Then we went to both weights but 90 degrees apart. So this is a different type of an unbalanced situation where the weights are interacting or causing the machine to vibrate a little differently. Finally, we put both weights at 180 degrees. So here the centrifugal force due to the unbalance is going to, one rotor is going to be working against the other, so to speak. Okay, here is a hotkey that says 2000 RPM. So that is actually the running speed of the machine. You can see down here in the picture there that we had a tachometer that was measuring the RPM of the machine, and so that hotkey is going to select the data for the running speed, and this is the ODS data, or this is called the first order of the machine. Now we actually took ODS data off of the ODS FRFs for 2000 RPM and then the second order, which is 4000. So in a machine like this, when there's unbalance, peaks will appear in the spectrum data at all of the orders. Well, not all, but certainly the fundamental, the first order, here's the second order, here's the third order, 6000 RPM. So we're going to look at the ODS data acquired from the machine at the first 3 orders. Here is another hotkey that says archive in the database. So there, when I press that hotkey, MEscope is going to start putting order data into the database so that I can trend it and look at it, and we will go to the console software then and actually view the data as it's being archived into the database. Finally, there's a hotkey here that says start over. So that kind of resets everything and starts the project or the demonstration going again. So this is a demo project which can be run by itself. All the information is contained within this VTPRJ of MEscope. Let's go back and look at how some of this stuff was defined. We've got a macro menu here, and we've also got what's called a Mechanicom menu. So again, when we enable one of these options, the surveillance series or the qualification testing series, we now can archive data into the larger database. So I just clicked on one of these commands called machine setup. So the database is organized on a machine basis. Now this option that I'm running here is the machine surveillance series option. So that's the MEC 1000 option added to MEscope. Didn't get to show that to you. That was in the price list that we couldn't display earlier. But here is a definition of a machine in the database. First of all, I give it a name. It's called Big Rotor. It's got a structure model, which is the one we're looking at here. It's animating. It's got what we call a monitored shape table. So what we put in the database are actually the MEscope STR, SHP, and in this case there is no spectrum data going in, simply shape data. But over here we can actually put in the data block data from, we can put in frequency traces, time traces, octave traces, but in this case we're simply going to store in the ODS shape data, and we'll be able to animate it on the model in console as well as here in MEscope. But let's just start this running, and we will do everything here in MEscope, and I'll show you some of the macro programming that's been set up in MEscope to carry out this demonstration. So I'm going to close that. We're all set up, and it says over here in database, this machine has already been defined in the database. So we've set up the FaCTs for this machine, and we've also archived some data in already. The model's already in the database, and what we call a footprint, or an example of the monitored and the animation shape table. Now, the other thing I need to do in order to archive data is I need to connect to the database. So here you can see that I'm already connected to the Mechanicom database. If I wasn't, I would need to select one of these files here, and this is called a database connection file, and it's got an extension DCF. So in order to get into a Microsoft SQL database, you need to have a username and a password. So that's one of the pieces of software that comes with one of these surveillance options. That is a database connection file manager, where I can create these DCF files, and then anyone running a console can have access to the database, and MEscope itself can have access to this database. So that's a protection mechanism for if this was part of a continuous monitoring program, where, for instance, you would want a consultant to look at some of your data, but you would give him permission only for, let's say, a week of time, and then his DCF file would only last for that time, and he would no longer have access to the database. The other thing we can do with this Mechanicom database is put it in the cloud, and we have clients already who are doing continuous monitoring with a setup like this, and talking to the cloud through a phone modem, and archiving data from MEscope in a remote computer into the cloud database. So anyone with a DCF file then can look at this data with or from the internet. Okay, so we're connected. I'm going to hit the reset button here, or the start over button, and we'll just see what it does here, and then we'll go look at some of these programs. You can see that it's put up a number of programs there, and then it's actually arranged the animation so that I can see a couple of shapes in animation. And if I look at these descriptions here, what I'm looking at is a 2000 RPM ODS, and over here the same thing. If I look at the animation sources over here, I can see that the unbalanced shape and the balanced shape are the two sources. And you can see they both have a label of baseline. So that is the balanced case for both of these. Now, and then up here are what we call modal assurance criterion, or MAC, and next to it is something called SDI, or shape difference indicator, and they both have a value of 1. I'm going to drag them down here to the bottom because they might not be that easy to see on your screen. So we get them out of the dark area, and now you can see that these two shapes, these are numerical indicators of the likeness of these two ODSs that are animating here in a comparison animation. And both of them are indicating that the shape is identical. Now the MAC, the difference between the MAC and the SDI are that the MAC tells us if two shapes, complex shapes, in this case they have 14 degrees of freedom, lie along the same straight line, Now that's a little hard to visualize with 14 degrees of freedom, but another way of saying it is that the two shapes are collinear. These are complex shapes. In this case, you can't see the complexity, but in a minute we'll see more of the complexity of these ODSs. The SDI, on the other hand, the shape difference indicator, is what the name implies. It's actually measuring the difference between the values in the two shapes. So not only would they be collinear, but the numbers in the shape components, the 14 components, would have to be identical for the shape, the SDI, to indicate a 1. So both these indicators go between values of 0 and 1. When they're 1, that means they're the same. When they're 0, they're very different. And a rule of thumb is that if the indicator is above 90%, then they're similar. So let's just push one of these other buttons here. Let's try number 3 here. This is an unbalance, a small outboard unbalanced weight. I'm going to press that button. And now you can see that I got a little more motion here. My unbalanced shape has shifted to the small outboard, and I'm comparing it to my baseline, my balanced shape here. And you can see that both of these indicators dropped in value. Let me slide my models up a little bit on the screen. I'm holding down the shift key and using the mouse. And so now the Mac is saying they're only 83% alike. The SDI is saying numerically they're only 72% alike. So this is a slight unbalance, and you can see just from looking at the picture that the machine is moving around a little bit more near the bearing block of the outboard bearing, because that's where we put the unbalanced weight. Let's go to the next one here. Let's see, number 4 is a large inboard. So in that case, you can see that there's a little more motion. Now the other thing that I've turned on here, which is one of the MEscope features, if I go under Animate, down here under Compare Shapes, you can see that I've scaled the animation so that the right shape is scaled relative to the left shape. So that allows me to compare the actual motion of the ODS on the right with the scaling of the balanced, or the baseline, what we call the baseline here, the balanced shape on the left. The other way I can look at this is up here. You can see in my shape animation source list, I have chosen the balanced shape on the left and the unbalanced shape on the right. And the macro program is actually taking data out of these 3 different cases and putting it into the unbalanced shape. We'll look at that in a minute. And then here is my model for the right-hand side. The left-hand side is always the one that I start the animation in. The right-hand side can be any other model that I have in my project. Let's go to the next case. Here's a large outboard. Okay, you can see that we're getting more motion now on the outboard end of the machine, and the Mac has dropped to 78, the SDI has dropped to 14%. So these numbers are quite different now because of the increased level of vibration. Let's go to the worst case here, number 6. This is both rotors having an unbalanced weight at 0 degrees from one another, which means that they're both at the same position on the inboard and outboard rotors. Okay, well, Mac value actually climbed back up, saying that these shapes are collinear in some way, but SDI has gone down even further, saying that numerically speaking, they're quite different. And you can see it in the picture, that the unbalanced weights are causing quite a bit of motion on the entire machine because of them coupling together being 0 degrees. All right, let's put them at 90 degrees and look at the unbalance then. So here they are 90 degrees away from each other. And you can see that Max still says it's 74% in this case. SDI still down there, 14%, very low. Correlation, another term we can use here is the correlation. You can look at both of these numbers as a correlation coefficient between the two shapes. And when it's 100, that means they're the same. When it's 0, they're extremely different. Let's go to number 8 here, where they're 180 degrees out of phase. And you can see that both those indicators are climbing back up because the unbalanced weights are kind of working against each other. So they're bringing the machine back into balance because one unbalanced weight is on the opposite side of the rotor from the other rotor. So that's the different cases. And then if I want, I can switch to, now this is the first order. Well, how do I know that? Here's something else that we're going to look at here in a minute. I'm going to go over here under macro, and this is a fairly new feature, so you're going to need the new software in order to write your own macro programs. Under macro, here's where I define the hotkeys, and I also define something called global variables. Let's look at the hotkeys first, because we've already talked about them. And this is a spreadsheet, just like many of the spreadsheets in MEscope. And here's where I defined all the hotkeys. So I can add hotkeys, I can delete them, I can execute them from here, and I can also pass them over to console. And we'll see where all these hotkeys that I defined in MEscope actually are going to show up in the console software, which is on the other side of the database, and I can control everything that goes on in MEscope from the console. So you can imagine that I've got a remote Mechanicom box, or what we call the Vibrant Portable Hardware box, with a computer and an analyzer and MEscope set up in the field to collect data on a machine like this. And I can control all of the things we're going to do here today from console remotely in that box. So here what we've been doing here, we had a hotkey, and one was called balance, small inboard, small outboard, and so on, all the way up to 180 degrees. Then we have 3 hotkeys for 2000, 4000, 6000. Here's one for archive, and here's one for start over. Now we give them a name, a macro program name. So we'll go look at some of these macro programs. These all exist inside of this MEscope VTPRJ. This project has a macro program, so when I push the hotkey, the macro program is executed, and then it finishes and it comes back. So there's some other things in here. I can pick icons. You can see we picked the hotkey 1 through 8 for the unbalanced cases, and then we pick some other icons. You can see there's a whole list of them that I can assign to a hotkey so that I can remember from the picture which hotkey was actually the one that I am pressing. So those are hotkeys. Now let's go and look at these RPM hotkeys, because I can switch and look at the ODS from the second order and the third order. And if I press, let's say, the 4000 RPM, now I'm going to be looking at, and you can see at the first or the second order, both Mac and SDI drop virtually to 0. So even though these pictures look pretty much the same, the actual numerical values are quite different. between the baseline at the second order and this unbalanced case. Well, how do I know what unbalanced case that is? The global variables are the ones that tell us what case we're actually running. So here's a little window that popped up over here. Let me make it larger so you can see. And I'm going to hold down the shift key or the control key and spin the mouse. So here are three global variables that define essentially the case that I'm looking at. So one of them is called the unbalanced case, and that's, in this case, we're looking at case number 8, which is the 180 degrees out of phase of the two unbalanced weights. Archiving data, the 0 says we are not archiving into the database right now. And the machine RPM is the 4,000 RPM case. So I can leave this little box up here, and let me just make it a little smaller, and we'll put it over here so we can watch these global variables changing as we press the various hotkeys. So let me go back and press the balance case. So you can see it switched to number 1, and we're still at 4,000 RPM. And so this is the balanced second order versus itself. And the indicators both went back to 1. So that's what we'd expect to see. Now I'm going to press, well, let's just jump ahead here. We'll go to the small outboard and see what it looks like. Look at these indicators. They both went very low. Even though we have very little amplitude here, you can see that the second order is the whole machine, and especially the base plate, is shifting back and forth, whereas over here it was more of a vertical motion. Now we have a horizontal motion of the base plate. We'll just leave it there. Let's try a large inboard. Now you can see the base plate is really starting to move around, and both indicators are saying that this is not the same shape data at all. And this is an indication of a resonance. We can actually, we haven't done a modal test on this machine, but if we took an impact hammer and impacted the base plate, we'd probably see a motor vibration or a resonance peak popping up in the vicinity of the 4,000 RPM. Perhaps not. It doesn't have to be at 4,000 RPM. It simply is getting excited because of the unbalanced force here. Let's go to the worst case, the number 6, where the two weights are at 0 degrees. And now you can see the base plate is just going crazy here. It's going nuts. Now, we've only got data where the blue icons are, and the rest of it's being interpolated. So can I really say that's what's going on at the other points? Perhaps not. This is a geometric interpolation between points, and certainly the shaft is not going to have a kink in it like that. But it's a good indication with this data from those points what's going on at this, severe unbalanced case. You can see that this accelerometer is really moving around. Okay, let's go to the less severe case, and again, I'm going to rotate them back so I can look at the base plate. You can see that flex in the base plate there. We're still getting some motion in the base plate. And the indicators are saying this is not at all the same shape. We can go to the 6,000 RPM and the same thing. But let's go ahead now and move on to the console and look at what is going on in terms of a trend plot, and then we're going to use the FaCTs calculation to see if we can actually identify these different cases. All right, I'm going to leave that alone and just start the console software. and we can go back and forth. Now I have the console software running in my computer along with MEscope, and I have the database installed in my computer. So I'm running everything right here in the computer. You can see MEscope in the background, and here is the console software. You can see it's the machine surveillance console, so that's the option that I have enabled here. And here are the same hotkeys showing up in console. So they have been passed in through the database to this particular for this particular machine. Now I don't have this machine. You can see that these are different machines in my database. These are different projects, MEscope projects that we've been working with. This one over here is a environmental monitoring project. You can see it's just a map of a building site in Toronto and in Canada. And here's a different rotor kit. Here's our familiar Jim beam, and we've got some other things in my database. I'm going to double click on this one though. This is the big rotor, and you can see that it's offline, and I've got some various things here. Let me just put these, well, let's just look at them one at a time here. I guess I want an icon. Icon. I'm going to look at my trend plot here. Let's put this guy down. We'll put them all down. We can open up all these panels and then we'll look at them one at a time. Okay, so they're all closed. I need to go back here and get some data back. Let's just look at a trend plot first. So what am I looking at here? This is showing me some frequencies. RPM, there's 4,000, here's 6,000, here's 2,000. So some data has already been put into the database for those different cases that we were looking at before. But now we can control everything right from here. So I'm going to go in here, and you can, this is what I'm trending out of the monitored shape table. I'm going to go pick one of the accelerometers. Let's go pick one down on the base, and I'm going to turn off the frequency, and now we can see these various levels of the accelerometer. This is the uniaxial in the 5Z location. Let me go back and show something else before we even get there. I'm going to go up here and show something called the machine tree. All right, here's the machine tree over here on the, this is showing all the different data that's in the database for the various machines. So I want to look at the one called big rotor. That's what we named this machine. There's no traces. We have things called gauges. Now the gauges are, we can put gauges on each of the shape components and the frequency and damping of the monitored shape table. So here is showing me the data that we acquired from the machine, the 14 degrees of freedom. You can see triaxial in the 0.1, 0.2, 0.3, 0.4, and so forth. And then the frequency and damping. Let's bring the model up and I'll just review with you what those points are. Okay, so here's a model and it's animating. Okay, I've turned off the photo model. I can put that back on so it looks like it did in MEscope. So this model now is animating in console, using the model and the database that's in console. Now here's something that's unique to the console. If I put the mouse near one of these accelerometers, I actually can see with some gauges the values of the accelerometer, the shape values from the monitored shape table. So if I start over here at 0.1, there are its values, and you can see that there's not only the current value but something called the baseline value. So I can set a baseline here in console using data from the database. I can say I want this data to be my balance condition, this is my baseline condition, and I can do the same comparison of the animation in console that we were looking at in MEscope. So we got all the same tools here, but we're on the other side, or we're looking at data in the database now. Okay, this one is showing me some different data. There's point number 4. This one here is point number 5 in the Z. Now it's got 1X and 1Y. I'm not sure why that is showing up there, because I don't have any X and Y data for that. I've only got Z data, and that's the one that we turn on, 5 in the Z. So that's what we're going to be looking at here in the trend plot. And then on the other side, we've got one more Excel over here, which is 6 in the Z. Now those are set up with animation equations. So I made a little mistake then in setting up exactly what we're looking at here with the model. But we can go back to MEscope and take a look at that. Let's set this up now that I'm trending 5 in the Z, and you can see it's in G's. I'll close this because we've seen what's in this particular machine. I'm going to go here. I like to use a different charting function. I like to use the bar chart. So here's a bar chart showing the vibration level at 5 in the Z. Now let's go use a hotkey, and I'm going to archive into the database. So I want to make sure that I'm archiving data into the database, and I should get a value popping up here. Okay, so there we go. And I'm at large 180 degrees. That was our last condition. Let me go back and set it to 2000 RPM. We'll start over again here. And I'm going to go with the balanced case. Okay, so you can see that the level went way down here. This is the 5Z motion. Oh, I'm still at 180 degrees, so is that correct? Well, let me click along here and see what happens. Let's go to small inboard. Not sure why that label is still saying that, but you can see the value as I go across here. I'm just going to, MEscope is archiving the data, and I'm looking at it now as we make each of those cases, archive each of those cases. You can see the 5Z is growing. There's 6Z, or there 5Z. Here's 6Z, and then this is case 7. Again, we're looking at 5Z, and you can see it dropped back down again, and then number 8. So this is simply looking at the vibration level. So there's all the cases for the accelerometer on the base plate at 2000 RPM. Now let's go look at something else. I'm going to take you back and we're going to look at something called the event log. And let me put this down so we can, oh, I don't know why that closed me out. Oh, I'm hitting the wrong button, that's why. Okay, so here's an event log. So what we've done here is pre-recorded in this event log. Anytime I look at some data in a trend plot, I can create an event. And then you can see here that these are operator-created events. Now, the other way we can create events is we can set up warning levels on the trend plot. And we have 6 different warning levels we can set up. And so we put the values in G's in there, and if a vibration level ever exceeds a warning level, then it will create an event. And there's some other tools in here. We can have the event send a message to your email or a text message to your cell phone. So if you've got this set up and you're remotely monitoring a machine, or it's just a machine in a plant somewhere, you can be notified whenever the vibration level on a particular accelerometer or any other data that you're measuring exceeds a warning level. But in this case, we did something a little different. We identified each of the cases as one of the known cases of unbalance. And so this would be a situation where you've got your machine balanced again, or you've encountered this unbalance in the past. You add that as an event to the event log, and then we can use the FaCTs calculation to identify that same case if it ever comes up again. So that's what we're going to do here. And with this event log, and let me show you how we do that. I'm going to open up the FaCTs, and let me put this down now, and we'll just look at FaCTs. This is the FaCTs bar chart. These values are SDI values, so exactly the same values that we were looking at with MEscope when we compared 2 shapes. These bars values here are comparing all the events that I've recorded in the event log with the current ODS data that has just been archived into the database. So how did we set that up? Well, let me go and open up this dialog here that says define bars. We have other storage FIFOs. Now, a FIFO is a first in, first out storage location for this machine. And I can set the storage up to save short-term storage, long-term storage, and then I have event storage. So when we talk about storage, we refer to a snapshot of data. A snapshot of data will be, in this case, the monitored shape table and the animation shape table. And if I had data blocks, then the data blocks would be saved in the database. So all the MEscope data, shape tables, data blocks, traces from the acquisition window, all this can be archived into this database. And now we're on the other side with console looking at some of these snapshots of data. So every time I hit a hotkey up here and tell MEscope to log more data for one of these cases, FaCTs will compare that data with the event storage where I've already identified the 24 different cases. In other words, the 3 orders and then 7 unbalanced cases for each order. And I did that in here. If we go and look at the bar, here's it says edit bar. So here is the gauges bar that's been defined. I call it the first order ODS. Down here you can see that it's been defined as a first order ODS. And we are I have selected all of these degrees of freedom. Now, if I were only interested in taking the data from the bearing blocks, then I would just select 1 and 2. And maybe if I wanted the motor, I'd select 3. And then these other ones are the base plate accelerometers, number 4 and 5 and 6. But in this case, we're selecting everything. And this probably should be labeled as not the first order, because we're going to look at the second and the third orders also when I archive data from them into the database. So we'll just call it 3 orders ODS, 3 orders ODSs. We could actually, there would be a more accurate description of what we're going to archive into the database. So let me show you what's going on here now. We're going to, you can kind of see the values. Let me make this a little larger so we can see the values coming in. The last one that I archived was 2000 RPM and case number 8. Let me go up here and press, so we've got 2000 RPM set in MEscope. Let's start out with case number 1. So that's the balanced case. And bingo, you can see that everything changed here, and the highest SDI value, comparing all of the events that I've stored in my event storage over here, comparing the different events, the highest one is the 2000 RPM. Now these are the other ones. You can see that this one here at the ODS for that 2000 RPM at number 3 is 72%. But we saw some of those numbers when we looked at them in MEscope. These are exactly the same numbers. The facts for the balanced case, case number 1 at 2000 RPM has a fax value of 1, and then so on down the line. So this is always the top 10. So I can have thousands of different cases. In this case, we have 24 events that we've recorded as those that we've identified, but I can compare my current data with all my short-term storage and facts. If the data hasn't changed, then it's going to correlate perfectly with, and I'll get ones all the way across the board here if nothing has changed. But you can see in this case the ODSs are drastically different. We saw that when we compared the shapes in MEscope. Let me go and try the small inboard. This will work perfectly for virtually everything. There it is, case number 2, 2000 RPM. Let's go try let's just try number 5 here. Okay, there it is. It put number 5 up there. Maybe you can see that a little better if I rotate it. And I can move it up here too. So let's just keep it right there. And then the first one is the one that it's identified with the maximum. And I'll rotate it a little bit. You can see that no other case is correlating as well. Well, case number 2. Here's case number 2 at 90%. So there's a fairly close correlation between the case number 7 and case number 5. The vibration levels for 5, in other words, the large inboard or the large outboard, compares pretty well with case number 7, which is the 90-degree case. Well, let's try that. Let's try 90 degrees and see. It should give us the same thing back again. Okay, so now it's saying case number 7 is the one that has the highest SDI value or fax value, and case number 5 is 90%. So those two cases, those two unbalanced cases, are very close, but they're still different cases as we've identified them. Let's go to the worst case again, the 0 case. And there it is now. This is very graphic because it's saying that extreme unbalanced case doesn't correlate well with any of the other unbalanced cases. They're all very low. And the only one that's high is the event storage of that case. Now we can go to the second order and try this out and see what happens there. So I just pushed the 4,000 RPM button, and again I've got case number 6, 4,000 RPM, and this is the extreme case. You can see that there's a little bit more correlation, 4,000, 2,000, 6,000 with these other ODS cases. Let's go to 6,000 and see what it correlates with. Okay, so there is 6,000. It's pretty much very strong. There's very little correlation with all these other cases in my event storage. So what FaCTs did is check all 24 shape values, ODS values, and compared each of them with the current one, the one that I just placed in the database. And so this is a little different than we looked at in MEscope, where we just could compare two shapes with one another, basically the baseline, the balanced case with the unbalanced. Here we're comparing all these different unbalanced cases, and we're seeing that FaCTs can clearly identify the correct case because none of the other unbalanced cases of the ODSs matches up with the current data very well. Except for the case, let's go back here, we had the one case here where the two ODSs were very similar. Let's see, this was case number 5 and case number 7. Those are the closest cases that correlate 90% with each other. You can see down here that it's 2,000 RPM, case 5, case 7. If I log case 7 into the database or archive it, you'll see that these two will switch. Now I've identified 7 and 5 is 90%, but all the other vibration cases are very low in terms of their ODS value. So, Brian, that pretty much concludes my demonstration of FaCTs. Let's go back and look at the macro programs, because the other part of this webinar was to show you some of the macro programs. Now, last month we actually went into some of the details, but I'm going to stop the animation here and well, let's push the start over button, because that arranges all the windows and actually runs one of the cases, so that wasn't very helpful, but let's put down this window. So here are some of the macro programs. This, typically what we do is write a main program. Let me make this larger, we'll just look at this, and we usually call it AAA main, but you can call it anything you want. And in there, this one positions windows and sets up some macro variable or some global variables. So this is the one that's positioning the windows. First of all, it's connecting to the database. This command up here in the MEscope window is connecting to the database. So that's this command up here. We looked at that before. So if we're not connected, running the start over will connect us to the database. Then it's positioning a number of windows. It positions itself, and then it positions the unbalanced shape table and some of these other windows. Then it comes down here and it defines the archive data. It sets that to 0. Remember, that's the one. If it's set to 1, MEscope will archive the data. If it's 0, it will not archive the data. And then there's one called machine RPM, so it's set to 2,000. These are the parameters for these commands up here. If a command has parameters, they show up in this other spreadsheet. So a macro program window just has two spreadsheets, one with the window, the command name. Down here, if it has parameters, that's where they show up. There's the third macro program called or the third global parameter called unbalance case. So I can pick any, this little drop-down menu shows me the global variables that I've already defined. And remember, we define them up here under macro global variables. So here's where they're defined, right here in this window. And if when I run this macro program, it will set those variables in there. And then it will run an unbalanced case program. So in a window called macro unbalanced cases, it's going to run that program one time. So let's go look at that. Unbalanced cases, here it is. And so this is the program that's doing all the work. And let's just go up here and see what it's doing. It's, first of all, it's doing a comparison, and that's a macro command in the window itself. Let me make this larger, you can see. So it's comparing variable 1 to 2000, variable 1 to variable 2. So it's picking up the machine RPM, which is a global variable, and saying if it's not equal to 2000 RPM, then go to a label called 4000 RPM. So here's the label right here, step label 4000 RPM. So if it's not 2000, it's going to jump down here and see if it's set to 4000. Well, let's assume that it is set to 2000 because I think that's what we just looked at. All right, it's going to go into the 2000 RPM shape table, the shape table called 2000 RPM. It's going to select a shape number 1. So down here it's saying select shape number 1. Yes, select it, unselect first. Now it's going to store that into, well, first of all, it's going to unselect all shapes in another shape table called baseline shape. That's the left-hand shape that we're animating in the animation. Then we're going to go back and say copy shapes to file. And what it's going to copy is into the baseline shape, it's going to copy shape number 1 because we've selected it up here. So then it's going to copy the selected shape in. Remember, if I select things, it operates on the selection. If I don't, it would copy everything. So it's going to copy shape number 1. Now it's going to go and select a different shape. Which one? The shape number is going to be the unbalanced case. So let's go look at that shape table. Here it is right here. And you can see that there are the 8 unbalanced cases. Brian has given me the hook here. He's saying our time is up. So I'm going to just show you a few more things here, and then we'll ask if there's any questions, if you send any emails with questions. But here is all of the recorded ODS data that we've been looking at in animation. So what this macro program does is it simply stores some data from one of these cases into the balance and unbalanced shape table, and then it's going to go down here to it's going to jump down to continue, and let's just look at what happens when it continues. It starts the animation. So in the STR window, it says, oh, first of all, it's going to put the RPM into the machine RPM into the substructure. This is going to take a little more explanation, but it's changing the RPM of the substructure so that it will rotate properly. Then it's going to start the comparison animation, and here it's telling it what animation source to use, what comparison source to use, and the comparison structure. So that's just a standard command in MEscope. Then it sets it relative to left shape. We saw that. It sets the amplitude of animation. It positions the windows so that we can look at them. Let me scroll this up so you can see. And then it comes down here and says, if I'm supposed to archive this data, if not, exit the program. So we jump down here and we exit the macro. Otherwise, we archive the data in the database. So if I go back here and just push one of these buttons, any one of them, you'll see this program will come running through here and execute all of these steps. Bingo, it just did it, and it started the animation for that particular case. All right, that concludes our discussion for today. Next month, I think we're going to do the same thing, so I invite you to come back and we'll do it with misalignment data. We've also tested this same machine. As I said, this original data was taken back in 2009, so it's already 6 years old. We also, the next year, I think in 2010, we did a technical paper doing the same, using the same idea, the same calculations on misalignment. And we'll see that FaCTs can correlate our archived data with stored data in the database and tell us whether in fact we have a misalignment case. So that concludes it. Brian, do we have any questions?